This conference will
Okay,
now be
right. So
recorded.
hopefully you can see. Can you see a big thing that says University of Southampton, which is the first slide? Does that look okay?
Yes, we can. Yes, we can.
Right,
Thank you.
Okay, right. So what I was going to talk about today, I was going to give a bit of an update on some of the permanent way research that we've been doing at the university. And it's an update because it's about a year since I did a talk actually in person at the Eastleigh meeting. So it's a few things that we've been up to since then. So I was going to cover sort of three things. The first was to say something about how we measure the deflection of the track as trains go across it, and also the support system stiffness for the track, which is quite often just abbreviated slightly ambiguously really to the track stiffness. And then I was going to look at how we can interpret some of those measurements to look at second bit is the effects of under track crossings on ballasted railways. And then the third one is the application of some of the techniques to the monitoring and analysis of long lengths of track. Because up until fairly recently, we've just really been sort of monitoring particular features, so transitions or the under track crossings. But what we'll go through are some of the techniques that we've developed to start to monitor lengths in the order of hundreds of sleepers, which is beginning to be quite interesting. So the first bit then is really to say something about the measurement techniques that we use, and we're particularly interested in the deflection of the track as trains go across it and the support system stiffness. So the next slide really just shows three fairly well-known track performance indicators. So the one on the left there, if I can try and get my mouse working, yeah, okay, right, okay, so the one on the left there is basically the deviation in the level of the track with position. So that's in millimeters over essentially tens of meters or hundreds of meters. And that's the sort of thing which is fairly typically measured from a measurement train. The thing is, it measures the deflected geometry. So although we might try to measure the position of the track in the middle of a car, which is well away from the wheels, we can't be sure of that. So what we really see is only comparable with other runs of a similar vehicle, because the different vehicle with a different speed or a different weight might well give us slightly different results. So that's really the sort of traditional thing that we measure from the measurement train. The things that we're interested in are the measurement of the deflection of the track under load, and we can measure that at the rail or we can measure it at the sleeper. Obviously, because you've got a rail pad in between, you're going to get a difference between those two, so it's important to know which one it is. And the other thing that we're interested in is basically the support stiffness, so or the stiffness of the track, which is what the train sees. And all of this is partly because a lot of the analysis that we do idealizes the track as a beam, which has got a bending stiffness that comes primarily from the EI of the rails, supported on a bed of springs here. So it's known as a beam on an elastic foundation, and that's the method of analysis that we frequently use. It has its shortcomings, but it's actually quite good for quite a lot of things. So those are the sort of three things that we'll be looking at. Not so much the track geometry, although we will come back to that later, but especially we're interested in the deflection under the train and the effective track support system stiffness, or the track modulus as it's sometimes called. Now, one of the things which it's interesting to note is that we talk quite a lot, I think, as a community about the track stiffness or the track support system stiffness. And we sort of feel that a high stiffness is good. But these are some measurements that we've taken over the years. So this just shows, and you can see there, we're talking about over a group of perhaps 10 sleepers. The movement range varies. So these are 4 different sites. Where the movement ranges from less than ½ millimeter generally. So a couple of these were probably sort of high speed sites, to between 2 to 3 millimeters. But and then if we look at the corresponding track system support system stiffness, what we can see is that the higher movements are associated with a lower stiffness. So the effective stiffness actually ranges between about 10 and 40, and that's in meganewtons per meter squared. But the important thing about all of these 4 sites is that the track was actually performing pretty well. And the hallmark really for most of those sleepers is that we haven't got any huge discrepancies in the stiffness. So it's not so much that the support system stiffness is high or low, it's that it is reasonably uniform. So that's actually quite an important criterion. This is just a picture of the new measurement train, and this is the sort of thing which is now done to measure. But what we get from that is basically a picture of the deformed geometry. So to some extent, the actual level is going to be a combination of where it is in absolute terms, plus where it moves to when the train goes over. And usually, as long as we're comparing like with like, that's absolutely fine. So what we're talking about now are measurements that we make from the line side. So we use a number of techniques, but especially digital image correlation, which is where we take a video of the deflection of the track and we analyze the image so we can pick up sub-millimeter movements down to sort of 1/10 of a millimeter or even less. We can also use geophones and accelerometers, which are discrete devices that we normally place on the sleeper, but sometimes on the actual rail. So the next slide is just a composite of those methods. So the middle picture here, that's a target that we use for the video monitoring. And the reason for that pattern is that it makes analysis of the image easy, and it means that we can pick up the sub-millimeter movements that we're often looking at. I think that little box is probably actually a MEMS accelerometer, but the cylindrical thing is a geophone. So these are the sort of expensive devices that we've historically used. The ballast, the thing on the right, bottom right, actually is a lump of ballast hollowed out to receive a MEMS accelerometer, which is the picture just up there on the top right. Basically, that will self-log, so it will take readings over a period of weeks or months, then we can come and retrieve it and we can work out what it's done. This is a video camera, and in the early days, the video was the most reliable method of measuring the deflection of the track as the train went over it, as long, of course, as you could get the camera in a position where it wasn't going to be buffeted by the wind, either due to the train or to the weather, or affected by ground-borne vibration. So those are the techniques that we use. I won't go through this table, but it will be there in the presentation if people want to look at it. They're different methods of measurement. Each one has got advantages and disadvantages. And this little table, which is actually taken from the track stiffness guide, which we helped produce a couple of years ago, goes through some of the advantages and disadvantages of these and other methods of measuring the deflection of the track as trains go across. So I'm not going to go through that in any detail, but it will be in the record of the presentation if you want to go and have a look at it. Now, a geophone, this is a trace of a geophone signal, a typical geophone signal as a train goes past. So we get a voltage as a function of time. The voltage is proportional to the velocity of the sensor. So as long as we know the calibration coefficient and we're in the linear range, which is quite important, then we can convert the measured voltage to a velocity. So we can get the velocity. This is the upwards or downwards velocity of the track that we're measuring as the train goes across. So you can quite clearly see the effect of each individual wheel or axle going over. If we integrate that, we get deflection. So this is the deflection trace. And you'll notice that the deflection appears to go up to what turns out to be a false datum. And then we actually get the deflections relative to this false datum on the trace here. I'm going to come back to that in a bit because that's quite an important part of the interpretation that we do. Now, as engineers, certainly as civil engineers, we're used to plotting things, as we would call it, in the time domain. So we plot the voltage or the velocity or the deflection as a function of time. But our signal processing friends quite like to plot things in the frequency domain. So what we've got here is a frequency response. So this is the relative amplitude of the velocity that we've measured, plotted not against time, but against frequency. So we can see that there's some sort of root frequency of perhaps a couple of hertz or something like that, and we're getting harmonics there. And some of those peaks are bigger than others. Again, it turns out this is quite a useful way of looking at the signal, and I will come back to that later in the talk. Now, more recently, we've started to use MEMS accelerometers, and these are good for high-speed railways. They're pretty much literally as cheap as chips. They can self-log, so you can leave them lying around the site for months on end, which you don't really want to do with a 600 quid geophone. So the MEMS accelerometer, you can see they're quite small there. We've used them on HS1. They just fit to the rail, if you like, or to the sleeper, if you like, wherever you want, or even in the ballast, as we saw on the earlier slide. and they give us a trace of acceleration against time, or this is acceleration against frequency. We now have to integrate the acceleration twice to get us the displacement trace, but you get the same sort of effect of this upward drift, but then what we're seeing is the deflection due to the passage of each axle. So in this case, it's around about 0.6, certainly less than a millimeter that we're seeing for that. I think that's a javelin train on that one. Okay. So I'm just going to say a little bit about the data processing and the interpretation. Now, this is quite mathematical, and I'm going to put some equations up, but I'm really not going to go into them in any detail whatsoever. Okay, so you can sort of have a nap during this bit if you want to do so. This is just back to the typical trace. So this is now the displacement against time, actually from a geophone. So we can see that there's an artifact of processing, which is that the zero appears to drift upwards, and then at the end of the passage of the train, it comes back down. So by calibrating this in the laboratory and in the field against video imaging and stuff like that, we've worked out that if you want to get the typical deflection under this train, you would look for this stationary region in the middle, and you would kind of eye it in to say that's your datum. This is roughly the maximum deflection. So in this case, we've got a maximum deflection under each axle of just under 0.4 millimeters. So that's actually quite time consuming, because you've got to take each trace and do it by using your own judgment by eye. And it also introduces a little bit of subjectivity into the process, which we don't really want. So one of the things that we've managed to do, and this is particularly my colleagues, David Milne, Louis Le Pen, David Thompson, we've managed to work out where is the zero position by considering what we call a cumulative distribution function for the measured deflection. So this is the next 2 or 3 slides are a little bit mathematical, so we're not going to worry about them too much. This is the beam on an elastic foundation. So essentially the thick black line here is the rail. This represents the support system by a series of springs, and we can have either a single load or moving loads. And the solution comprises basically a shape function, which gives us the deflected bowl, the deflected shape of the track underneath a single load. And then there is a load function, which has got a whole series of loads representing the passage of each individual axle. And when we combine those, we get a solution for the deflection as a function of time, which depends on the track system support modulus, which is this thing in red, which is effectively the stiffness of the springs, the bending stiffness of the rail, the EI of the rails, and then the position and the number of wheels for a speed V and at times T, and that depends on the characteristics of the vehicle. So that depends on the train speed and the distance that the loads are apart, and then also the FN is the axle load. So this is the sort of shape of the solution that we get. And it looks complicated, but this is probably about the simplest sort of thing that we can do. The important message with this is that there is a shape function, and then we have to take into effect all of the individual loads because they all get added together. Now, it turns out that if I look at the theoretical deflection from that particular model underneath a single point load, it's sort of far enough away from the single load, there's no deflection, we get a little bit of rebound, we then get the maximum deflection under the load, and then it's symmetrical. And if I look at this in the sense of saying, if I were to choose a random deflection, what is the probability of this random deflection being greater or less than a certain amount? I can plot that as I have done on the right, where basically the probability that is going to be greater than the maximum deflection is 0. The probability that is greater than the minimum deflection is 1. And I get this quite distinctively shaped curve, which has that sort of elbow in it there. And that elbow corresponds to the true zero position. And that just drops out of the maths. Now, the clever thing is that I can use that to work out from a real signal where the true zero position is. So that this is a real trace for a javelin train, and you've got the stationary region there. And what we might well do is sort of eye it in. This is the theoretical solution, so it hasn't got that upward drift, which is an artifact of the signal processing. And if I look at that probability curve, the real solution is the one in light grey here. the actual solution, sorry, the actual data gives me the one in black. And you can see that essentially the one in black is just moved across to the right a little bit, which is the displacement of the 0, and smeared a little bit. And it turns out that if I took 0.7 on the vertical scale, that near enough locates that knuckle or that elbow. And that's a good indication of the true 0 position. It might vary a little bit. So what I've got there is it going between about 0.68 and 0.7 something or other, 0.76 maybe. And actually it doesn't really make any difference to the deflection that I measured at my 0 position. So the great thing about this is that you can automate this. So you can take a real trace like this, and rather than having to eye it in every time, you can run it through an algorithm that works out where mathematically the likely true 0 position is. I've tried to explain, what is 6 months work in the space of about 3 minutes. But there's a paper there for anybody who is really interested, but it's quite pokey signal processing. But the long and the short of it is that I could take any train passage and very quickly automatically obtain a typical deflection associated with that train passage. So how does that work in practice? This is a trace from a MEMS accelerometer in terms of acceleration. That's in the time domain. This is the frequency analysis. This is the double integration to get displacement. I run this trace through the algorithm and I pick up for this middle bit a single point which represents the typical deflection. Then the graph on the right, every red cross actually represents the typical displacement of a single train. So this is a particular site that we were monitoring, and you can see that we have got pretty good agreement from one train to another. Yes, there is a range, but they're probably different types of train. And the other thing is that we've been able to monitor this data over a period of 6 to 8 months. And so essentially to try to extract all of that by hand would just be incredibly time consuming. So it's that little automatic algorithm based on the knuckle in the theoretical curve and identifying where that is in the practical curve, the measured data curve. That's what enables me to get these little data points here. So I can pick up what is the typical deflection under a train, and I can plot lots of those and get a very good picture of how the track is performing. Okay, so the second clever thing that's been done, and again, this is my colleagues Louis, David Thompson, is to estimate the support system stiffness from the ratio of harmonic peaks, but without having to know the train load. And again, that sort of drops out of the maths. It turns out that if I now plot things in the frequency domain, the displacement, and these are the different frequencies of the displacement, is essentially a function of the shape function, which drops off with frequency, and the pattern of load. So this goes back to what I said about the beam on the elastic foundation analysis, that we've actually got two components. There's a sort of basic shape, which is this one, which drops off with frequency, and then there is the series of loads, which is the one on the right, which is associated with the train. And they combine to give us this pattern of displacement peaks when we plot it in the frequency domain. And what we can see is that the effect of the displacement bowl here is that it tends to attenuate the magnitudes of the peaks at higher frequencies. And the other interesting thing is that these three different values of the shape function depend on the stiffness. So if the support stiffness is low, the displacement bowl is deeper and more spread out. If the support stiffness is high, so it goes from 10 to 20 to 40 meganewtons per square meter, the displacement bowl starts to be tighter and also less deep. And that means that the effect of the support stiffness on the relative magnitudes of these peaks is significant. So that fact is what we use. And it turns out that if we look at the signatures for different trains, so this one is an 11-car Pendolino, this one is a 5-car Super Voyager, there's a 6-car Turbo Star, and there's a 4-car Electro Star, and each of these trains has slightly different signatures, and that comes about because of the relative geometry of the wheels and the axles and the bogies. But it turns out that the ratio in all cases of the 3rd to the 7th harmonic is
William, we appear to have lost your vocal. Just bear with us, folks, whilst William gets his sound back on.
Hello, William. We've lost your voice there. That's better.
Or even from measuring the deflection.
We missed about 30 seconds of that, William. So we missed the start of that slide. That's it. You were just explaining.
Okay.
You were just explaining that the ratio from the third to the seventh harmonic was something, and that's when it stopped.
Okay. Okay. So basically, the ratio on the previous diagram. So
that's
essentially,
yes.
These are the sort of the harmonic. Okay. So if I take the third and the seventh, and I look at the ratio of the third to the seventh, it turns out that is a function of the track support stiffness, but not a function of the actual wheel load. The nature of the ratio depends on the type of train. So I can work out a relationship for these 4 types of trains, or each of these is for a different type of train. And I can look at this velocity or the displacement or even the acceleration amplitude ratio between the third and the seventh peaks as a function of the system modulus. So if I know that I've got, let's say, a pendolino, which is this dotted one here, and I know that my ratio of the third to the seventh peaks on my signal is 1.5, I can infer that I've got a track support system modulus of about 35 meganewtons per meter squared. So again, that's quite a clever little bit of maths, which enables us to interrogate the signal in a way which is probably not what one would have immediately thought possible. Okay. Right, so that's the maths and the theory out of the way. What I'd like to do now is go on to look at how we can use some of these measurements to try to assess the effects of, first of all, under track crossings, and then secondly, we will go on to look at very long lengths of track. So I'm sure you're all going to be fairly familiar with under track crossings. So they might vary from this, which looks like a fairly innocuous orange pipe just running underneath the rail. So there's the orange pipe carrying a cable, and maybe that's not going to have too much effect on the track support. We can sometimes get these things like brick culverts that go underneath, and then they can be problematic because they can represent either a hard or a soft spot below the track. Sometimes we try to modify bearers. So this is a concrete sleeper, which has been got a trough within it to try to carry a cable across it. This is another version, so that's a hollow bearer, and so that's a signal and telecoms cable going underneath there. And all of those can have an effect on the behavior of the track. So what we're going to look at now is the use of the data that we've obtained to try to identify behavior and defects associated with under-track crossings. So the first case study is a rigid under-track crossing. So it is this one here. So those are 2 under-track crossings. They're actually great lumps of concrete. Oh yes, they're identified on yours. So there is the first one, there is the second one. And by the time they get to be underneath the track, they're probably well over ½ a meter deep, covered in ballast. And one might have thought that that was actually going to be enough for them not to be noticed. But in reality, there were issues at that site. So this is the sort of white spotting that you get, which is fairly typical of excessive movement of the track. And I think that was either just before or just after the crossing. And it was one of those problematic areas where running the tamper through didn't really help. So just a routine tamp all the way through didn't really sort this problem out. So at the site, there was around about ½ a meter of ballast, and we've estimated some stiffnesses here because we're going to look at some finite element analyses. Sub-ballast about 0.2 meters, subgrade, and then chalk. So it was actually on HS1. So those are the sort of ground, those are the ground conditions at the site with some indicative stiffnesses. And if we look at the sleeper movements, we saw very little movement on the under-track crossing, so less than a millimeter, so probably less than ½ a millimeter. Then immediately after the crossing, we see that we've actually got these movements of the 5, 8, 8 millimeters or so, then dropping back to about 5. And it's this large movement of the sleepers which is causing that massive white spot that we saw in the earlier picture. So clearly there's something unpleasant going on. This just shows a whole series of measurements. This was the intervention, this vertical line here, and that was a targeted repair which included the provision of undersleeper pads. So what we can see is that the deflections over the crossing were initially very small, and the deflections after the crossing were initially quite large, between 4 and 8 millimeters. After the intervention, we've put the undersleeper pads on. So actually the deflection over the crossing has increased, but that's a controlled increase because it's got the undersleeper pads. It was to try to soften up the effects of that lunk of concrete under the track. But then the targeted intervention has brought the deflection as we come off the crossing down to around about 1 millimeter, which is probably sort of where it should be. So all of these basically would be represented, that would have been obtained as a typical movement under train passage using the signal processing techniques that we talked about earlier on. So to try to understand what's going on, we built a simple, it looks complicated, but it's relatively simple finite element model. So it's 2D, so it just represents conditions on the center line of the track. We just had 2 carriages going across, but we did represent the primary and the secondary suspension. There was a length of model of, I think, about 165 meters. We had 3 layers representing the natural soil, the embankment, and the ballast, or at least the underlying soil, the subgrade and the ballast. We could put in sleeper pads, and then there was backfill below an under-track crossing. And there was this is a sort of generic schematic because it potentially looks at a number of sites. But in the first case, this under-track crossing was concrete, so that was very stiff. And we put the trains across in the first site at a velocity of 83 meters per second, which essentially corresponds to the speed on high speed HS1. We ran the models twice, once without any gaps imposed below the sleepers. So that's as if everything was perfect. And then in the second model, we put in some gaps to try to reproduce the measured deflection that we'd actually observed. So this is just a schematic of the finite element model. You can see the rail, the sleepers, the ballast. This is the under-track crossing, these 2 orange things, the subgrade and the underlying soil. So basically, it's done using a commercial finite element package. There's nothing terribly clever about this, and it's all linear elastic. So if we look at the calculated deflections, this is just running a train across with the track in perfect contact. What we can see is that there is a small reduction in deflection over the under-track crossing. The deflection as we go onto the regular rail is just a little bit greater, but there isn't anything like the variation that we saw in reality. So there isn't any reason why the difference in support stiffness between the under-track crossing and the natural ground should have made the difference that it did. If we then put in some gaps below the sleepers to try to mimic the displacement that we measured, we can see that nearly all of that massive displacement that happens after we come off the under-track crossings is actually due to the gap below the sleepers. So nearly all of the displacement is due to the prescribed gap. And of course, I'm sure many of you will sort of realize. So the other thing is that the stresses, again, with no gap, there isn't that much disruption due to the difference in stiffness of the under-track crossing. But with the gap, that's when we start to get large variations in the stresses that the sleepers are exerting on the ballast. And then the other thing is that if we look at the acceleration of the sleeper, we can see that with no gap, it's all fairly uniform. But with the gap, we're getting massive accelerations of the sleeper. So of course, what you will all be probably very aware is going on is that we've managed to get voided sleepers here, and the sleeper is crashing into the ballast and causing that damage and the white spotting that we had seen. But what the finite element analysis tells us is that this is not because of the difference in stiffness, it's because a gap has developed because of a difference in permanent deflection, which is quite an important point. So the second case study was a flexible under-track crossing at a place called Somerton. So it's this type of thing. So it's basically they're cable ducts, and they come in different shapes and sizes. And I think the one that we installed was a 3x3, so it was that one there, I think. That's 3x3. I can't quite see it on my screen. So that's it going in. So this is being installed on an existing site. So it's a Cubis flexible under-track crossing. And then again, after it had been installed, we got this classic white spotting of the ballast, indicating that things were not really as they should be. So in this case, we've again got, well, 0.3 meters of ballast bedding to the UTX. Then we've got an embankment of firm clay and the underlying ground. So that's the indicative profile with the stiffnesses that we used in the finite element analysis. So now if we look at the sleeper movements from the geophones, these are the measured movements. What we're seeing is a big movement as we go over the under-track crossing. So this is now on the crossing itself, going up to 8 millimeters, but on either side, it's more typically between 1 and 3 millimeters. So again, we built a finite element and model. This is now the flexible under-track crossing, which is there. So we've got the sleepers, the rails, the various different soil layers. And as before, we can run a train over it. And this, I think, might be a video if we're lucky, and we'll see a train going across, and we'll see red coloured zones indicating where the stresses are high. So you can see there the stresses associated with the passage of each train. Okay. And this is just it slowed down a little bit. So if we now look at the calculated displacement, again, we see that even though the UTX might be a bit softer, it's not actually giving us any greater displacement. So that we shouldn't really expect to see that massive displacement over the UTX that we actually measured. But when we put a gap in, we can see that again, most of that big displacement of up to 8 millimeters over the UTX is actually due to us putting a gap in. So again, the big deflection is not associated with a difference in support stiffness as such, it's associated with the development of a gap. So again, we can look at the model, and this shows us the effect of having the gaps in. And what we can see is that we get a much bigger deflection as we go over the crossing. So that's exaggerated, of course. And we also actually tend to get a stress concentration. So again, to represent this, this is it just a little bit slower. So what we're getting there is that we're getting the big deflections and a disruption in the stresses due not to the different stiffness of the under-track crossing, but due to the development of gaps below the sleepers. So again, if we look at the stresses below the sleepers, we can see that with no gaps, it's fairly uniform. But when we put the gaps in, we get a huge variation in the stresses. And it is that then which starts to damage the formation even further. Again, similar thing, if we look at the acceleration of the sleepers, we can see that with no gaps, it's all fairly uniform. But with the gaps in, we get big sleeper accelerations, which just hammer the hell out of the ballast, to use a technical term. Okay, so, oops, I thought that might be a video, but that video doesn't seem to work. Never mind. Right, okay. So for the under-track crossings, we've used our methods of track displacement measurement to assess the performance of both a stiff and a more flexible under-track crossing. Tamping through the defect didn't sort it out, so they tried a targeted repair. And the finite element modeling of the perfect support conditions actually didn't really give very big variations. It only gave small variations in movements and stresses where the ballast was in perfect contact with the sleepers. And to reproduce the measured behavior, we had to insert gaps. So the measured bad behavior is not actually due to a difference in stiffness as such, it's due to the development of the gaps. So that's quite an important thing to notice. And then the other thing from the FE analysis is that the deteriorated state of the track started then to lead to non-uniformities in the stress distribution. So you end up with a runaway situation where a bad situation gets worse. Okay, the last bit of the talk is about monitoring and analysis of long lengths of track. So again, just for the record, there are some papers where this is described in more detail. So this was a length of track of about 300 sleepers where we measured the level and the stiffness and the deflection. And we also carried out some vehicle track interaction modeling like we did with the under-track crossing. So the stiffness and deflection survey was using the little accelerometers, which we've seen before. So that's just a picture of them mounted on the sleepers. The absolute level we had to measure using a total station. So that had to be done manually. And if we look at the data of deflections, so this is over a 350 sleeper length, this is the deflection that we get under a Javelin, this is the deflection under a Eurostar, and this is the deflection under a Volaro. And you can see that there are some consistencies. So round about sleeper 180, we've obviously got something weird going on with deflections of up to 5 millimeters. But back here, whatever is going on at sleeper number 10 was actually nothing like as bad under a Javelin as it was under a Eurostar or a Volaro. So that's an interesting thing, that the behavior is slightly different with the different types of train. Probably not too surprising, but it possibly means there's some threshold effects going on. Now, if we use our measurements to infer the track support system moduli, again, we get slightly different answers, although actually fairly similar patterns with 3 different trains. Now, if our model was perfect and the whole system was linear, we should get the same answer in each case. The fact that we don't is probably a combination of the model not being perfect and also the response of the system and the trains themselves not being totally linear. But actually, the broad pattern is not too bad. What's interesting is that all of the discrepancy, or most of the discrepancy, is actually in wavelengths which are greater than about 40 meters. So this is to a log scale. This is a wavelength of the deflection of 100 meters. So that's going to be 10, 20, 30, 40. If I only take the data to the right of this, there's actually a lot more consistency between the 3 trains. So that's a sort of interesting thing in itself, because what it's telling us probably is that beyond a wavelength of about 40 meters, what we see is probably a function of the train just as much as it is a function of the track. So again, we carried out some vehicle track interaction modeling, again 2-dimensional. The vehicles were modeled with secondary and primary suspension. We did try to model the actual vehicles, so the 5 coaches of the Javelin train, and we carried out 4 simulations. So in the first one, we used the measured level, but we assumed a uniform modulus, support modulus of 30 megapascals. In the second simulation, we assumed that the track was perfectly level to start with, but we used the measured moduli. In the third and the fourth simulations, we used the measured level, the measured moduli, but in the fourth simulation, we put in some gaps, some voids, to try to reproduce the displacements that the previous models hadn't been able to do. So if we look at the results of that, these are the simulations for a constant support modulus of 30 meganewtons per meter squared. And if we look at, this is the deflection that we get, and this is the inferred modulus. Now, if everything was perfect, we should just return a uniform 30 meganewtons per meter squared modulus here, which we obviously don't. So again, that's an indication of some nonlinearities and the lack of perfectness of the model. But it's not too far. I mean, it is hovering around about 30 megapascals. So if we now look at the other simulations, so this is basically all of these now are using the measured support system modulus. So with the first one, we are comparing the measured data, which is the thinner line, with simulation 2, which is a smooth initial track level. The next one is the measured data with simulation 3, which is the measured initial track level. And the final one is the measured data with simulation 4, which is the measured initial track level with some voids in. And what we see is that actually between 1 and 2, there's not a huge difference. So actually what that tells us is that really, in terms of getting the sleeper deflection, the initial track profile is not that important. What is more important is to try to get the support stiffness right. And also, if we think we've got voiding, we need to reproduce voiding, because we're actually managing to match some of these otherwise unmatched peaks by the introduction of voids. So you can see that happening there, there, and there. So these are going to be the effects of putting in the voids. If we now look at the inferred support modulus, what we can see, so this was all essentially the measured one is what we input, and then this is what we get back out of the analysis. And what we can see with that is that the best fit is probably simulation 3 and simulation 4. What that means is that actually reproducing the initial level of the track is in this case important because it improves the fit. This is the one where the initial level of the track was assumed to be smooth. But in these two, we got the measured initial level as well, and it gives us a better fit with the input support stiffness. And then finally, these are the simulated wheel rail contact forces, which we can't compare with measurements. Basically, this top one here is the measured initial track level and a modulus of 30 megapascals, just assume constant. This is the measured initial track level, the third one, and the measured modulus. The fourth one is the measured initial track level, the measured modulus and imposed voids. And actually, the difference between any of those is not that great. The one which is really significant is where we have got a smooth initial track level. And what this tells us is that the modulus is not really that important for getting the wheel rail contact forces. The thing that matters for that is to get the initial track level right. So to summarize all of that, it tells us that basically the modeled track deflections don't depend very much on the unloaded track level, but they do depend a lot on the track stiffness. And the modeled wheel rail contact forces don't depend very much on the track support stiffness, but they do depend a lot on the unloaded track level. So that kind of tells us what is important to reproduce if we're looking at the behavior of the track system. So just to finish off, a little bit about future monitoring. And again, there's a reference for that. So we've had some success in gluing an optical fibre to a rail. So this is an optical fibre glued along there. And what we can do is we can send a pulse of light along the optical fibre. It goes along and it comes back. And we can then get a measure of the strain. And that's plotted as what we call a waterfall diagram, where this is the distance along the fibre as a function of time. And the colour indicates the strain. So basically the yellow and the green are areas of high strain. So what we're seeing here is that you get mirror images because essentially the fibre goes out and back like that. So essentially the train would go along in time like that. So the passage of a wheel going along comes across as a sort of diagonal line like this. And what we can see is that at certain locations, so at around about 8 meters here, which is mirrored there on the way back, we've got this yellow spot indicating that there's probably a track fault because we're getting excessive bending in the rail. So this is quite a good way of probably in the future trying to monitor the track in some considerable detail. Okay, so to make some concluding comments, it's feasible now to carry out deflection monitoring of long lengths of track using discrete sensors, the accelerometers. Future sensors will probably include optical fibers attached to the rail, but possibly, could we interrogate the telecommunications fibers that are a meter or so away? That's quite a challenge because the signal gets distorted through the ground. Then for the section that we investigated, the unloaded level dominates the loaded level. So basically where it is to start with is pretty much where it is when the train's on top of it, with very few exceptions. A variable support system stiffness is needed if we're going to measure the measured sleeper deflections. So the deflection of the sleeper under load depends on the support system stiffness. And then finally, if we're interested in calculating wheel rail contact forces, it's important we get the initial track level right. And actually that's all consistent with the findings that we had from the under track crossing, that it's not so much a difference in stiffness that messes you up. It's when you start to lose contact between the underside of the sleepers and the subgrade. So there are some references which will be in the slides that will be available that I will whiz through. A lot of people support the research, to whom I'm grateful, but thank you all for listening. So hopefully we've now got time for some questions. I'll stop sharing my screen, okay, and hand back.
William, that was a fantastic talk, and absolutely wonderful that you managed to get through so much content so concisely. Thank you very much. My colleague, our secretary, Ken Newell, is going to moderate the questions and answers. If you want to ask a question of William, We have to finish no later than 20 to 2, because there's another meeting going on straight after this one. If you wish to ask a question, press your little speech bubble and Ken can see that you want to ask a question. I can't, unfortunately, because I'm using the wrong sort of device.
Another option for anybody not happy to speak, you can type the question into the speech bubble and Ken will read it out on your behalf. Or if you've got an immediate question, you might like to unmute yourself and present it to William.
So could I outrageously jump the queue then in that case? And William, what do you think the implications are for what you've said to us in terms of where we have an under-track crossing, what we should be doing with under sleeper pads between the rail and the sleeper, and the frequency of packing the track to remove voiding?
So I think perhaps I could say a little bit more about both of those cases. So the first one, the hard concrete one, was on HS1, and I think that when Niall Fagan, who some of you might know, saw those results, he kind of immediately increased the minimum depth of an under-track crossing on HS2 to so I think it is interesting that even at half a metre depth they can have an effect. But I think part of it is that if there possibly there's an issue in the first place and it's never properly addressed, it will always be a problem until you go in and sort it out. The idea of putting the the undersleeper pads was really about trying to sort of even out the stiffness that the train sees. I think our finite elements analysis says that shouldn't really be a problem, but I suspect that one of the problems with the finite elements analysis is that if we don't have something in the model, we won't see it in the analysis. So one of the things that's very difficult is to pick up the gradual accumulation of differential settlements over millions of cycles. So I think it is definitely worth thinking about trying to sort of even out the stiffness through the crossing. I think it's also definitely worth trying to get it right to start with. And I think the other thing is that if you do start to get a problem, to go in and do the targeted repair, probably by hand packing the few sleepers afterwards. What they did on HS1 is that they broke up the sort of hard pan that had developed at the bottom of the ballast. Because that was one of the problems, that you ended up with this sort of hard pan that had developed, and then it was always there. So they broke that up and then really sort of did the ballast. But those repairs that they did on HS1 have lasted years, whereas the TAMPs were lasting a day and in some cases made things worse. The other one, we were asked to get involved because the concern was if the crossing is too shallow, they wanted to make the crossing not so deep so that digging the trench was not as onerous in health and safety terms. And our feeling was, well, you don't really want to worry about the crossing, you want to worry about what it's going to do to your track. And I think that part of the problem they had there was that they had this whole series of a maintenance contractor who was sort of in the process of going bust and all the rest of it. And I think they never really completed the installation properly. I also do have a slight worry about whether, if you're trying to sort of compact the backfill above something which is itself quite lively, you probably can't use normal methods of compaction. So I think that one would have to look very carefully at how one compacts the backfill above a flexible crossing. So I think the messages are, I think keeping them deep is probably quite good, although that starts to be expensive in terms of installation. And I think it's really about making sure that if you backfill above a flexible crossing, it's got to be really properly backfilled. If you backfill around a hard crossing, again, it's got to be properly backfilled. And it's probably, I think, about getting it right from day one. And if it isn't right from day one, you've probably got to be prepared to go in and do a sort of targeted hand intervention to make it better.
Thank you very much.
On a similar subject, actually, Bob Hazel asks, how does depth of ballast cover impact on the effect of the UTX? And also, is there a desirable ballast depth, and would this vary with speed and axle loadings?
Yes, so I think one might think that there ought to be, but I think that probably what our investigations have shown is that there are other factors that are more important, such as the quality of the workmanship and making sure that everything is adequately back compacted. And then I think that if you get everything right, you could probably get away with a fairly shallow UTX. Obviously not totally shallow, but I suspect that to make it so that the depth of cover was sufficient to make up for bad workmanship or bad installation, it would be so deep it would be unfeasible. So it's probably more about. So I'm not aware of any guidelines along in the way that Bob has asked about. I think what the work shows is that a relatively shallow depth can be okay, but a relatively deep depth might not be okay. So I think the short answer is it's difficult, and I don't think there's any hard and fast rules.
Well, thank you, William. Andy, I don't have any more questions on the chat line at the moment.
Okay, thank you, Ken. If anybody would like to ask William a question, please go ahead.
So I mean, I think, you know, sort of possibly going back to Bob's point, I mean, I think what you really want, you want to avoid that excessive deflection, because I think once the excessive deformation starts, it then just leads to a hammering of the ballast and the development of voided sleepers. And then the whole thing just gets away from itself. But I think that it is possible to get, you know, it is possible not to have that excessive deflection, even with a fairly flexible crossing, and even with a even with a relatively shallow depth of ballast. So I think that the second one would have worked fine if it had been installed properly.
So just reflecting back on that, William, what you're suggesting is that the quality of installation and compaction above the and around the UTX is a mitigation against the development of voiding under,
yes, I think that's
under
right.
the passage of trains.
That's right, and I think you probably end up one side or another of the line, and on one side it will start and get worse, and on the other side it will probably be fairly stable. And you know, you might not know how it's going to perform until, you know, a few days or a few weeks after the installation's been complete. But I think the message is probably that if there is a UTX which is giving trouble, it probably needs a fairly thoughtful bespoke solution.
Yes.
Rather than just running the tamper through.
Yes. If I may, could I just ask one more question then? Are you in a position, do you think, to draw any conclusions yet about the use of on-track machines in track without a UTX, in terms of how it's lifting some places and not others, and what the long-term effect of that sort of maintenance is? Or is that too big a thing to speculate on?
Well, we've done a fair bit with HS1, and their problem sites are not all UTX. So some of them were, even there was one place where they had a change from monoblock to duoblock sleepers, and then there are others where they come off a slab onto conventional ballast. And there was another one which was a not particularly well designed bridge expansion joint. And I think that they all have, you know, the characteristics are kind of fairly similar, which is that once the problem's developed, you probably need to, you almost need to sort of cut it out in a way. So for example, going in with a Kango, breaking up the development of a hard pan is a reasonably common feature. So getting rid of that and sort of starting over with something which is right. But none of this was over a huge length. It really only had to be over a few meters. And that did seem to sort it out. So the targeted repair did seem to do it. So, you know, I think that the machines that do long lengths are great if you need to do a long length. But I think probably when you end up with this sort of almost bespoke transition zone UTX type defects, if they don't work initially, they probably need a bit of individual TLC, I suspect.
Excellent, thank you very much.
One note from Bob Hazel, just a comment that historically the depth of ballast required has been associated with the future ability to allow ballast cleaner cutter blade to pass over the UTX.
Yes, I mean, I think possibly one thing I could add is that we've done some work where, if you've got, like we did some work on a level crossing over in Sussex, and basically that was a problem because they could never really tamp very close to it. So you do end up with then these places which are never maintained and also potentially end up as fixed points, whereas the track around it gets lifted and so on. So you then end up with a geometry defect and also a place that's never been maintained, and I think that can be problematic. Paul Ebbott has said, is it transitions into and out of a UTX input? So potentially it is. And I think in the case of the concrete one, it wasn't the UTX itself that was the problem. It was actually just the transition out of it. So I suspect that if you've got a UTX, which either because of itself or because it hasn't been properly compacted over, tends to be softer, that's probably where the problem will develop. But if you've got a UTX which is hard, I think you've got the potential for something to develop probably coming off it. Where you end up with the transition onto the softer material. So, again, the finite element analysis showed it's not the difference in stiffness in itself which is an issue, but I suspect that a softer material is more susceptible to developing differential settlement, and it's the development of differential settlement which becomes an issue. But there's an interesting comment about the depth of ballast being that to allow a cleaner. Yeah, I mean, I guess that in the cases that they were looking at, they were probably looking at having the same depth of ballast or possibly above the backfill. I don't think they were looking at reducing the depth of ballast, particularly on the crossing. It was probably really the depth below the bottom of the ballast that they wanted to reduce in the case of the plastic one.
Thank you very much. It's
I guess,
really.
Perhaps if I might, one sort of slight frustration is that I think we could have got a lot more out of, especially that second one, but actually getting back to do further monitoring turned out to be very problematic. And it's the sort of thing that we've gone 70% of the way, and actually with a bit more effort we could have got a lot more information out of it, but by then whoever was in charge of the job had sort of lost interest, and that I think might be a plea to members that actually if we can just, sometimes it's quite difficult to close these things out because the people that you're working with either move on or lose interest.
Thank you. A point well made. Any more questions, Ken, on your typed question line?
No, there aren't. No, the only, just to make the point that all the online presentations are in the PWI website in the technical hub and under PWI online. So that's where the presentation will find itself.
Andy, one from me, Mike Talbot. There's nothing in there that says a more a stiffer under-track crossing is better than the flexible, is there? Is there anything in here that tells us we ought to be a little bit more prescriptive of what contractors put in?
I think the answer is no, because I think they can both give problems, and it's not, almost the stiff one is that was one of the ones that caused the problems in the first one. So I think what it comes, I think what you might want to do is one might want to try to manage the stiffness seen by the train. Although there are people who vehemently think you shouldn't put undersleeper pads on over a hard concrete crossing. So there's clearly an element of disagreement in the industry about that. And I think that the problem with the flexible one wasn't that it was flexible, it was just that the stuff wasn't properly compacted over it. As I say, I have one thing that I'm not sure about, which is whether it would ever be possible to compact, or at least using conventional means. Because you can imagine it's a bit like trying to compact something on a very spongy surface, that it just doesn't work because it's always vibrating itself. But the problem is actually the vibration during compaction that stops it from compacting. But I don't know that. That's a kind of random thought. But I think that those plastic crossings, if properly installed, would be fine. So there wasn't an issue with the crossing not being stiff. Although obviously it's easier to make It's easier to make it less stiff by putting it under sleeper pads than it is to stiffen up something which is in itself a soft spot.
Thanks.
Very good. Right. I think that's been a really helpful end to the presentation, William. Thank you very much for those really insightful answers to the questions. That was extremely interesting, and thank you very much indeed for giving the talk. Because we're online, you can't hear the generous ripple of applause that is coming from our attendees for the talk today, but I can assure you that it is happening in an online virtual sort of way. And thank you very much again for giving your talk.
Oh, thanks everybody, and thanks everybody for listening and for your questions. Thank you.